All right, so we're going to talk today about polynomial functions. You'll find that a lot of the things that we do in Precal is a repeat of Math 3. Some of you may not remember enough Math 3 to even know it because it's been so long. Others of you, let's see, I know Lewis just came from Math 3 and Reese and Molly just came from Math 3, so like you may feel like you're doing the same thing over again. It is because there is overlap in the standards. So you are doing some of the same stuff again. We go further with the new stuff than with the old stuff than it does in Math 3. But it's similar stuff that we're doing over again. I usually find that's really good because a lot of the topics that we do were the harder stuff from Math 3 that maybe you were a little shaky on anyway in that class. So polynomial functions. You learn about in Math 3. A polynomial function is any representation equivalent to the analytical form, and then they give you this big, long mess of stuff here, where n is a positive integer, a sub I is a real number for each I from 1 to n, and a sub n is non-zero. Whenever we look at this, it can be really sort of overwhelming because they use all these subscripts and letters, and it seems complicated. But notice you have x to the n power right here. Then what's the next one after it? X to the n minus 1, x to the n minus 2. And then it goes x squared, x, and then there's no x at all, right? So n could be any number. If it is 7, then that's your that is your like highest exponent that you're looking at. So then you also have a sub n minus 1, a sub n minus 2, a sub 2, a sub 1, a sub 0. When we use subscripts, we're just saying like this is my first a and my second a and my third a and my fourth a and so on. So this is just a coefficient, right? All your a's, let me highlight with some different colors here. A's, oh, that's not my highlighter. All your a's are just coefficients right here. So whenever you see this in practice, those are numbers. They're 7, they're 10, they're 2.5, things like that. Your n minus 1, n minus 2, that 2. There's not an exponent here, and then there's not even an x at all right here on this last one. But when there's no exponent, we can put a 1 right there. And there's no x at all back here, but if I put x to the 0, that means there's 0 x's there, right? And it just, x to 0 is just 1. So all this is telling you is your exponents are just in decreasing order for that. So, so like with what we're given here, our leading term would be a sub n x to the n power. It is just your term with the highest exponent. Okay? And then your highest exponent is called your degree. So whatever that n value there is, that's your highest exponent. So you might even want to write over here, highest exponent. And then the leading coefficient is the coefficient in front of your highest degree term. So that would be a sub n. Okay, these are just numbers here. I like to walk through this given to you in this manner because textbooks are going to write things like this in them. When you go to college, depending on what type of professor you have, you may have professors that are like super analytical. I know a lot of times professors that are from different countries are going to really like focus on some like analytical stuff, and you might not see numbers. They use variables for everything in that. So I just wanted to walk through that to sort of help you picture like what it's talking about. When you see this in actual problems, it is very simple, So like for A, we're supposed to give the leading coefficient and the degree. So the leading coefficient is the number out front. A coefficient is just the number in front of the variable. And it's the leading coefficient is the coefficient in front of the highest degree term. So on this one, it is just 3. And your degree is going to be your highest exponent, which in this case is 4 for that. So whenever I'm looking at this, Jericho, what is the leading coefficient for B? It's a little tricky. Look very closely. It is almost 7. It is -7. You got to keep that sign with it. There. And then, Jericho, what's the degree? It's 3. Okay. I'm almost glad that Jericho fell for the trick right there, because it has to be in standard order. That second one is not in standard order. So you got to pick out the term where you have the highest degree, which is this one, and then so your leading coefficient would be that -7 for that. Okay. C is a little bit tricky too. So let's see for this one. Autumn, what do you think the leading coefficient is? Yeah, you don't have a lot of options, so 4 would be the best guess there. What about the degree? It's 0. Very good. Because there is no x. So if you put an x there, the only way it could equal 4 is to put x to the 0 power. Because anything raised to the 0 power is 1, so it would just go away. So very good on that. Okay, questions? Okay, so let's talk about different types of extrema. Okay, I don't know what you guys had in Math 3. Have you guys seen the word extrema before?
Maybe like a little bit, but
yeah.
I don't remember much about it.
Extreme. I know you did this, but you may not use the word extrema. The extrema are the graph are maximums and minimums. You have seen maximums and minimums, right? Yeah. You may or may not have called them extrema. I'm pretty sure I did not call them extrema whenever I taught Math 3, because there is no sense in me trying to put extra words in there that they need to remember. But you may sometimes see maximums and minimums called extrema. It is an all-inclusive term that includes both maximums and minimums. So they like to use it because they can just use one word to ask you for both for that. So there are 2 types of extrema that you are going to be looking at. There are relative extrema, also sometimes called local extrema, or there are absolute extrema, which are also sometimes called global extrema. They may use either one of these terms interchangeably. Relative and local are going to be used interchangeably, and absolute and global are going to be used interchangeably. So they may use either one. So a polynomial has a relative minimum or relative maximum where it switches between decreasing and increasing, or at an endpoint if the polynomial has a restricted domain. This drives me crazy right here. In calculus, endpoints can't be relative extrema, but in Precal they can. And why they did not get together and decide we're doing it this way, guys, between the Precal and the calculus, I don't know. But you're typically going to see relative extrema when you switch between decreasing and increasing. That probably, I guess it says switches between decreasing and increasing, so that could be either way, decreasing to increasing or increasing to decreasing. Or it can also be at an endpoint if you have restricted domains. I don't like that because I don't like that the endpoints are possible, but it's fine. We'll do it that way, since they said we need to. For for your absolute, okay, so for your absolute extrema, first of all absolute extrema are also relative extrema. So whenever you have a relative maximum or minimum, it also could be an absolute maximum or minimum. Because look at our definition right here. Let's go ahead and find these. Local minimums and local maximums is what they are asking us for. So if we're looking for local minimums, that would be any point where we switch from decreasing back up to increasing. So that would happen right here. It is also going to include this endpoint right here, because that is a low point there. So we would have local minimums at x equals -4 and x equals 0.
So it's not the y value, it's the x value.
Well, the way they have phrased this, they're asking us, it says local minimums at x equals. So it's wanting to know the x coordinate for these. We're going to learn in a minute that the maximum or minimum is actually the y value. They don't usually ask you for that for relative maximum minimums. It's usually absolute whenever you see that. So typically, they'll give you x values here for local. It maybe could ask you for the y values, but in this case, they want the x values. Maximums, we would have over here. Maximums are places we switch from increasing to decreasing. So here and over here are both going to be maximums. And we're just going to give the x values where those occur. So that's -2 and x equals 3. Okay, so if you look at what they tell you about absolute extrema, they tell you of all local maxima, the greatest is called the absolute maximum. The least of all local minima is called the absolute minimum. So pretty much when you find all of your relative maximum or minimum points, those are your candidates for being your absolute maximum or minimum points. If we are looking for local or absolute maximums, we're looking at these 2 points right here, and we're looking for which one is the absolute highest, right? And in this case, what is my absolute maximum? It's at x equals 3, right? Now, notice how they give you this. They say absolute maximum equals blank at x equals blank, okay? So your absolute maximum or your absolute minimum is your y value. It is the y value that is the highest or the lowest. So your absolute maximum point, or absolute maximum in this case, would be 2. And that happens at x equals 3. So you have to be very careful with wording of the question to know whether it's looking for the x value or whether it's looking for the y value. If it just asks for absolute maximum or absolute minimum, it's looking for the y value for that. Sometimes it'll ask for the x value where the absolute maximum occurs. Then it'll be looking for x's. What about absolute minimum for this? -4? Does that seem right? Anybody want to argue with that? -3.
Oh, what?
So -3 would be your y coordinate at x equals -4. Everybody agree? You shouldn't. Anybody want to argue that that is wrong? You would never say it's negative infinity, but your thinking, I believe, is correct. Why are you saying negative infinity? It has an arrow over here on the end. So if you look over here at this end right here, you've got an arrow. So although it doesn't look like it goes any lower than this point right here, it keeps on going down forever and ever and ever, right? So when that happens, rather than saying our minimum is negative infinity, you don't really want to say that because a minimum tells you there's a lowest value. Can you ever get to negative infinity? Right? Like, you can never get there, right? If you got negative a gazillion, you could do negative a gazillion and one, and that's lower, right? So since you can't actually get there, what you'll do is you'll just say none for that. There is no absolute minimum for that one.
So the endpoint doesn't matter for absolute, it's just local?
The endpoint would matter if we didn't have the arrow over here on the end. So like if this was a dot right here and it ended, then you guys would be exactly right. The minimum would be -3. The x-coordinate would be -4. So if that ended, you would put the lowest point on the graph. But because we have that arrow, this point over here at -4 is not actually the lowest point. Does that make sense?
Yeah.
So absolute means it's the very, very, very lowest point on the graph. So it can still be a relative or a local minimum because it is lower than the points around it. But whenever you have like arrows on the end of your graph, that is usually going to keep you from having at least one of them. Like in this case, because that goes down forever. Anytime it goes down forever, you can't count this as your minimum because there are points lower somewhere on the graph there. So usually when you see arrows on the end of the graph, it's going to keep you from having at least one of the absolute maximums or minimums, sometimes both for that, because you won't have a point that's like your lowest point. Does that make sense?
So for the local, because it's restrictive, you can't say it's none.
Right. So local doesn't have to be the lowest point on the graph. Local is lower than the points around it. So like, for example, this point right here is definitely not the lowest point on the graph. Over here is lower. Right here is lower. Right here is lower. There's lots of points lower than that. But it's still a local minimum because where you switch from decreasing to increasing, this point is lower than all of the points right beside of it. So it can be a local minimum. Just can't be an absolute. Okay? All right, so if we are given this graph, okay, it's asking for relative maximums, minimums right here. Notice we've got arrows on the end. In fact, if we take this reasoning that we just had, these arrows on the end are going to keep us from having an absolute something. Which one are we not going to have? We are not going to have absolute minimum. None. Because this graph continues on down forever. So we can have a relative minimum, maybe. We might not have that either. But we definitely do not have an absolute minimum because of those arrows. So let's look at what we've got. We are looking for a relative minimum. Do we have a relative minimum? It does not switch from decreasing to increasing. And the endpoints, we don't have endpoints on this one, right? Because they keep on going forever. So we also have no relative minimums for this one. Okay. We do have a relative maximum. Okay. Hank, what is the x-coordinate where the relative maximum occurs? 1. Very good. This relative maximum that we have right here, so that's our max, is also our absolute max because it's the very highest point that we have on the graph. So if you have an absolute maximum, it is also a relative maximum every time. Kind of like a square is always a rectangle, right? Not all rectangles are squares, but all squares are rectangles. Not all relative maximums are absolute maximums, but all absolute maximums are going to be relative for that. So in this case, though, it's asking us for absolute maximum is blank, and it happens at blank. So we would say it happens at 1. What is the absolute maximum value? 3. That's where we put our y-coordinate for that. Okay. For B, I'm going to check my endpoints first and see if I've got any arrows. That's a good, because it's tricky. There, I've got an arrow that goes down in this direction. What does that mean I'm going to have or not have? We're not going to have an absolute minimum. So I'm going to put none here because this goes down forever, right? I'm looking for relative minimums, relative maximums. Let's look for minimums first. Minimums are going to be places where you switch from decreasing to increasing. It's lower than the points around it. That's going to happen right here at this point, which is going to be at x equals -2. Okay? Relative maximums are higher than the points around it. So, Chandler, where am I going to have relative maximums? 3, definitely. Okay, anywhere else? -4. So, now I'm going to tell you, in calculus, you would not call that a relative maximum. But they tell us in pre-cal that we're supposed to count it. So, don't remember this next year. But for right now, yeah, you just wouldn't list it at all. But they tell me in pre-cal we're supposed to call that a relative maximum. It is higher than the points around it, though, so that I can still go with that logic, right? So both of those places are relative maximum. All right, now I need to think about my absolute maximum. So whenever I'm looking at that graph, Marley, what's my very highest point? What is my absolute maximum? Okay, it is at 3, so it's going to be at x equals 3. What is the absolute maximum value? 2. So we'll say absolute maximum is 2, which happens at x equals 3. Okay, you guys do C on your own real quick. Okay. Oh gracious, let's send this thing again where it's. Well, let me write. There we go. Okay, let's see. Kendall, what did you guys get for relative minimum? All right, -3. Why is it not on your right? What have I done? X equals -3, so right here. And what was your other one? X equals 3. Okay, do you guys agree? I think that looks good. Okay, let's see. Deanna, what about the relative maximums? Okay, x equals 5 and x equals 0. So, -4 is the end point right here. It's higher than the points around it. 0 right here, you switch from positive, increasing and decreasing. That's definitely one. And then over here at this last end point. Very good. As I said, -4, 5, and 0 for that one. Okay, Aiden, what is the absolute minimum value? Okay, -3, and occurs at -3, right? So the first -3 comes from the y coordinate. The second -3 is your x coordinate. So this point right here is that absolute minimum point for that. And then, Alyssa, what about for the absolute maximum? Very good. At x equals 5. Perfect. So that absolute maximum is over here furthest right endpoint. Now, when it comes to absolute maximums and minimums, you would definitely do it that way in calculus. Just in calculus, I wouldn't call that a relative. Even though, I guess if I say that all absolutes that have to be relative as well, I have to go think about this some more to think which way I want it to be. But I'm pretty sure in calculus that you don't call that a relative. There. In our class, it is so. All right, so some fun facts about polynomials that we need to know. Number 1 says between two real zeros of a polynomial. What is a zero of a polynomial? That is an x-intercept. So it's a place where it crosses the graph crosses the x-axis. There must be at least one blank blank or blank blank. Let's reason through this. Okay, so we've got a graph. We have two x-intercepts. So let's say we got one right here and one right here. What is going to have to happen between those? Like if we go to draw this line in, this curve in, you're going to could have a highest point there, right? Or does it have to be a highest point? I could go a different direction. I could draw it in like this way. It could be a lowest point. So I think it's going to be a maximum or a minimum you have to have in that case. Is it going to be relative or is it going to be absolute? Okay, it's going to be relative because the rest of the graph could do anything. Like this could go way up here and then back down, right? And then, over here, this could go way back up. So it might not be absolute, but you're going to have a relative maximum or a relative minimum. So you have to have at least one relative maximum or relative minimum. There. Okay. The next statement is going to be about polynomials of even degree. So this would be like x to the second, x to the fourth, x to the sixth. So this is pulling back from some things from Math 3. Really talking about like your end behavior of the graph. So like whether the ends both of them go up, but they could go like this, or they could both go down. So if you have even degree, what do you know about the end behavior of your graph? Both down or both up, right? They go in the same direction. So if you know that this end goes down over here and this end goes down over here, what would that graph have to have? It's got to have an absolute maximum. Now it might do crazy stuff in between, but it has to have absolute maximum because both ends go down. So there's got to be a point they got to the very highest. So it's either going to have an absolute maximum, or if you know both of these ends go up, what are you going to have? Absolute minimum. And we know that like that absolute minimum is technically also relative. So we could switch the words absolute with relative, but we want to be as specific as possible, right? So we want to fill that in with absolute. Okay? All right, so next thing we're going to talk about is points of inflection. A point of inflection occurs when a function changes from concave up to concave down or from concave down to concave up. At a point of inflection, the rate of change of the function changes from increasing to decreasing or from decreasing to increasing. So, so we're looking at concavity changes. Sometimes these are a little hard to tell from the graph, to tell exactly where it changes from concave up to concave down. You will most of the time see these as multiple choice, so that I won't give you options that are really close to each other. So for example, 3, they're asking us to find any values of x where g has a point of inflection. Okay, so we're thinking about where we're switching from concave up to concave down. So if we think about like tracing this graph here, on this part of the graph we are concave up, curved up, right? But somewhere in here, I would say probably at x equals -1, it looks like we switch to concave down or curved down right here. And then if we go all the way over, it looks about at x equals 1. Now we switch to being curved up again. So your points of inflection for this graph would be at x equals -1 and x equals +1. Knowing exactly where it changes, especially if it is not like a nice graph made, it's sometimes a little difficult to tell, but you should be able to get close enough to that. All right, for B, it says for each of the following intervals, determine if the rate of change of G is increasing or decreasing. Explain your reasoning for each answer using features of the graph of g of x. So they're not asking us now about g being increasing or decreasing. They're asking us about the rate of change of g being increasing or decreasing. So if we think we've made that same chart several times, if we think about what g looks like compared with our rate of change of g. If our rate of change is increasing, what does that tell us about our graph of g? Concave up. And if our rate of change of g is decreasing, then g would be concave down. So they have asked us about several different intervals here. I'm going to erase my highlight here so I can re-highlight. 3 to 4 would be from x equals 3 to x equals 4. And we want to know if the rate of change of g is increasing or decreasing. What would we say about this, increasing or decreasing rate of change? It is increasing, because we're concave up there. So we would say rate of change of g is increasing because g is concave up. So from -4 to -3, we would be looking at -4 to -3. That would be this section of the graph. Let's see, Molly, this Molly, what would we say for that? Is our rate of change increasing or decreasing? Increasing, and why? Right. So our rate of change of g is decreasing because g is concave up. So like your rate of change, as Molly said, it looks like it's going down, but it's not really because it's negative, right? If we think about drawing in those little like slopes right there, it's actually a little hard to tell. It's pretty steep, but it's getting a little less steep, right? But because those are negative, that value is actually increasing. Oh, sorry. Yes, it's increasing. I wrote that wrong. Sorry about that. You get it together. Yeah. Your answers have to be the same. Thank you for catching that. Okay. For -1 to 1, you're looking right here on this graph. On this section, you are concave. Your graph is concave down. So we would say the rate of change of G is decreasing because G is concave down. And then for this last piece right here, we've got from 1 to 2, which is this little piece right here. Is our rate of change increasing or decreasing here? Increasing. Okay. So, rate of change of G is increasing because G is concave for that. Okay. The last one is a calculator active problem. You guys don't have to get out your computers for just this one problem. I'll just put this up here on the screen. So we're going to have, I'm going to use C of X because Desmos just is a little better if you use X's sometimes. Okay. So notice right here, it gives you some information that you need to know. It tells you for 0 to 3. So we only care about this graph between 0 and 3, right? On Desmos, you can restrict this by doing squiggly brackets, 0 less than or equal to X less than or equal to 3. And then it will only give you the part of the graph that you need to see. So that is helpful so that you don't have extra pieces that you're looking at. It gives the number of cars in a parking lot at time t hours can be modeled by the function given here. Based on this model, at what time does the number of cars in the parking lot change from increasing to decreasing? So where on this graph does our number of cars switch from increasing to decreasing? One, probably a little past 1, right? It's here at that maximum point. And when it's Desmos, you can just click on it and point at it. So, oh, it's counting by 2s there. I said 1, but that is count by 2s, isn't it? So 2.44. Now it's asking for the time, not the number of cars. So we would say at t equals 44564 hours. Now, a note about rounding on the AP exam. And this will be what I go by for pretty much the whole class. On the AP exam, all of your answers must be correct up until at least 3 decimal places. So this is in general my policy as well for anything that I give you that needs to be rounded. You can keep more decimal places, you just cannot keep less than 3. So if you gave me 2.44564, I will count that as the correct answer. Or you could say t equals 2.446 hours. You could round it to 3 decimal places. That would be correct. You could even do 2.4456 that would be fine. You can keep more than 3 decimal places. You cannot keep less. I will say the exception is sometimes in Canvas, you have to round it to 3 decimals, and that is just because Canvas won't grade it right if you put extra decimals sometimes. And I'll try to warn you of that if that's the case. But as far as what I will take, you can always keep more, never keep less than 3 decimal places, unless it doesn't have more than 3 decimal places for that. Okay? All right. So, questions? Okay, good. We finally